Nonlinear dynamics. So we're now in chapter 6. We kind of blazed through chapter 5 about linear systems, but we're going to start using them now in this chapter where we talk about nonlinear systems again, but in 2 dimensions. And so our first topic is to look at fixed points of this 2-dimensional nonlinear system, x dot equals f of x. And so first let me just do a little theoretical part, and then we'll touch on an example or two. And I'll also mention an application of population biology. So here we go. All right, so we've got a fixed point, x star, y star. And we'll write it in components as x dot is some function of x and y, and y dot is some other function of x and y. And remember, a fixed point for a 2-dimensional system would mean that both x dot and y dot are 0 there, representing an equilibrium state of that system. And now we would like to know what kind of fixed point is it? If you remember, when we talked about linear systems, we had various types of fixed points. There were nodes and spirals and saddle points and centers. So can we say the same kind of thing when we go to nonlinear systems? And it turns out that typically, yes, that typically the nonlinear systems we're going to study will have fixed points that look very similar to what we studied in linear systems. That was one reason we studied linear systems. More exotic things are possible, but they tend to be sort of rare. So let me not get into them at this point. Anyway, so let's talk about this fixed point and try to classify it. That is, what type is it? And so let's consider small deviations away from it, which we'll call u and v. So u of t would be x of t minus x star. And v of t is the same thing for y. Y of t minus y star. So these, we've sort of moving the origin of our coordinate system to the fixed point, and we want to see what happens in the neighborhood of that point. Let's derive some differential equations for the u and the v, given what we know for x and y. So, for example, if we calculate u dot, then since x is a fixed point, x star is fixed point, we'll just get x dot. And x dot, we said, is f of x and y, which, in terms of these new variables, would be f of x star plus u, y star plus v. And so far that's exact. No approximation made at this point. But what we would like to do is say we're thinking about small deviations, and so we're going to use this linearization idea that we talked about earlier in 1-dimensional systems, but now generalize it to 2 dimensions. And so this is about the one place in the course where you need to remember the multivariable chain rule. That is, well, I guess I should say really the Taylor expansion for a function of 2 variables, or really just the linearization, in fact. So what is the expansion of this about x star, y star? It's going to equal f of x star, y star, plus there will be a term that looks like u times the partial of f with respect to x, evaluated at the fixed point x star, or I mean the vector x star. And then we also have a term that is v times the partial of f with respect to its second argument, y, also evaluated at the fixed point x star. And then assuming that this f is smooth enough, I could keep going and have it, expand the whole thing in a Taylor series. So there will be higher order terms, which I'll just write as HOT. That's not hot. That just means higher order terms. So these are, terms that are, they would look like things like u squared or uv or v squared. These would be quadratically higher order terms. And you could imagine cubically higher order terms like u cubed and so on. But the point is, all of these, we hope, are negligible compared to the linear terms u and v, because u and v are tiny. And so when you square them or cube them, they'll be even tinier. All right, so that's the hope, that we can ignore the higher order terms, just like we did earlier. And then similarly, we would get that v dot. Oh, by the way, maybe you're noticing that this first term, which looks like a constant, f evaluated at the fixed point, we know that's 0, right? Because we said that's the definition of a fixed point, that x dot and y dot are 0 at the fixed point. So this term is not there, that's gone. And so these two linear terms, linear in u and v, are the dominant terms. Also, it sort of looks like there are functions here, these partial derivatives, but keep in mind that they're just numbers, right? They're functions evaluated at a specific point. So they are really effectively just numbers and don't depend on time. The only thing that depends on time is the u and the v. So anyway, v dot, same kind of argument, would give us partial g with respect to x evaluated at x star. That's a number times u, plus partial g with respect to y evaluated at I put the parentheses in the wrong place. Okay, so I mean to say evaluated, boink, at the fixed point, x star, close the parentheses, times v, plus, again, higher order terms. And so collecting all this into a more compact notation, it's nice to write it as a matrix times a vector. That is, what we're saying is that u dot v dot, regarded as a two-dimensional vector, is this matrix of partial derivatives, partial f with respect to x, partial f with respect to y, partial g with respect to x, partial g with respect to y, all evaluated at the fixed point in coordinates x star, y star, times the vector uv, plus the higher order terms, which in matrix notation we might write this as a vector u dot equals a matrix A times a vector u, where A refers to this matrix up here, and here's the higher order terms. So A is going to come up a lot in the course. That's the thing we're going to call the Jacobian matrix. And it's the linearization of the vector field, gives the linearization of the vector field about a fixed point. So do we have any questions so far? Yes?
Are you evaluating df and dg with respect to x and y both at x?
These are x star vector. I've been fooling around with the notation. Sometimes I write x star vector, meaning the point x comma y star. So either notation is okay. Is there another question? Okay, so now if we neglect the higher order terms, then we have the linearization of the system about x star. The linearization, or the linearized system, are two terms used for it, about the fixed point x star. And so you can probably guess that that's what we're going to do, but that is, we are going to neglect the higher order terms. We should be careful about that because sometimes it can cause trouble. That is, we should ask the question, does the linearization give qualitatively correct dynamics near x star? We don't expect it to be quantitatively correct. We've ignored terms. So, it's not going to be exactly right. But the question is, will it, since we're interested in qualitative things in this course, we're trying to get a sense of the phase portrait. Like, by neglecting those very tiny terms, can that somehow change a center to a spiral, or could it mess up a saddle and make it something else? That's the kind of question we're asking. And the answer turns out to be pretty nice. There's a theorem, which I'm not going to prove, but if you were taking a rigorous differential equations course, this would be something that would occupy some time to prove the next statement, which is that the answer is yes, actually it does give qualitatively correct dynamics if the fixed point happens to be a saddle, a node, or a spiral, according to the linearization. That is, if the linearization says that this point is a saddle, it really is for the full nonlinear system when you don't neglect the higher order terms. And likewise with a node or a spiral. But there are other cases which are borderline cases, in a sense I'll explain in a minute. The borderline cases, which would be a degenerate node, a star, a center, or non-isolated fixed points. Those can be altered. Meaning that the small nonlinear terms that we neglected could actually make a difference in these. These are sort of very delicate cases. And so let me try to explain first, why do I call them borderline? It's not a psychiatric diagnosis. It just, it's literally, they're borderline in a certain diagram. You may remember that when we drew a classification of linear systems, let me just sketch that diagram for you. It was the culmination of our work in the last lecture. Maybe you remember this picture that we drew where we had, how'd it go? We have the determinant on this axis, we had the trace. So recall this picture. Then there was this parabola going through here, which was tau squared minus 4 delta equals 0. And we said that saddles live over here. And the nodes, this would be a stable node down here. The unstable nodes are up here. And unstable spirals are here. And the stable spirals are there. So all those cases are robust. They are not delicate. They're the cases which live in nice big open regions, and you can perturb them a little bit with nonlinear terms and they can take it. They don't change. The borderline cases literally live on the borderlines between regions. Like this line, you'll remember, is where the non-isolated fixed points live. Or this line is where those funny kinds of nodes, the degenerate nodes or the stars, live. And finally, the centers live on this borderline here. So those are all thin, infinitesimally thin. Those are just curves instead of open regions. And so points that live on there, the fixed points that would be classified according to the linearization as one of those borderline cases, they can be affected by nonlinear terms. And so let me show you some examples of how that would work. But hopefully it's sort of plausible that one would be more delicate than the other. So let me do an example of that. Was there a question about something? Okay, so this example is first to make this point about the delicacy of such borderline cases, but also it'll show a technique that we're going to use from time to time. So it's a pretty contrived example that is contrived to come out very nicely, artificially nicely. So here it is. X dot is minus y plus some constant a, x squared plus y squared. And y dot is x plus a times y times x squared plus y squared. All right, so there's some nonlinear system. Notice it's got cubic nonlinear terms like x cubed and xy squared. You can see by eyeballing it that the origin is a fixed point for this. So 0, 0 is a fixed point. And if you calculate the Jacobian for this, you'll find that the A comes out to be 0, -1, 1, 0. So there are two ways we could calculate that. One would be sort of ponderous and just following what we did above. Maybe I'll do an example of that. So like suppose I wanted to calculate why is this entry 0. I could say, well, I'm supposed to calculate dx dot dx, or the way I had written it earlier, df dx. So whatever, dx dot dx, just taking those partial derivatives, derivative of minus y, that will be 0 because we're doing a partial with respect to x. Then I would get 3a x squared from the x cubed term, and then there'd be plus a y squared. But then that's supposed to be evaluated at the fixed point 0, 0, which gives us 0. Okay, so that's how I calculated this term. And then you could calculate the other three similarly. The other way you could instantly see what the Jacobian is just by thinking about what does the Jacobian mean. Remember, it's supposed to be the linear part of the vector field. And here, when we're linearizing about the origin, we earlier had this notation that we said u is equal to x minus x star. But if x star is 0, u is just equal to x when x star is 0. In other words, the u and the x are really the same object when you're linearizing around the origin. And so to see what's going on, you could just replace the x by u and the y by v, and then neglect any cubic terms in u and v, which will just be these. So just eyeballing it, you can see that the linearization will be u dot is minus v, v dot is u, and these will be negligible. So I don't know if you followed that or not, but if not, you can always do it this way. Anyway, so there's our Jacobian, and let's try to classify that. It has a trace, which remember is the sum of the diagonal terms. The trace would be 0 plus 0, which is 0. And the determinant would be 0 times 0 minus 1 times negative 1, which comes out to be positive 1. So on our diagram, that's about here, or that point is 1, and this is, remember that's delta, this is tau. So it's sitting right there. That is, according to the linearization, it's a center. So 0, 0 is a center according to the linearization. And in situations like this, we would say it's a linear center. That's what we'll mean by a linear center, that the linearization predicts it's a center. Now, in fact, that is not really correct, except if we're very lucky and A happens to be 0. Remember that there's a parameter here, A. According to the linearization, this thing is a center for all values of A. The linearization doesn't even see little a. It's not appearing there. So for all A, according to the linearization. That's not going to be right. So let's see what's really going on. All right, well, how are we going to analyze a nonlinear system? We don't have many techniques at this point. In fact, I don't think we have any, really, for a two-dimensional nonlinear system. So, but maybe just by being on math team in high school, you can see a move. Right? I mean, when you see x squared plus y squared, that gets your polar coordinate mojo working, right? Yeah. And, you know, it seems like, come on, obviously you want to go to polar coordinates if you see x squared plus y squared. So let's try that. That is a good instinct. That is, let's use a better coordinate system. Let's say x equals r cosine theta and y equals r sine theta. And and we're thinking of r and theta as functions of t. So we want to derive equations for r dot and theta dot. R is a function of t, theta is a function of t. And we want to convert our x dot, y dot equations into polar coordinates. So there are a couple ways of doing it, but the efficient way is this way. You can say x squared plus y squared. Actually, can I comment on how you would probably do it if I don't tell you the trick? What you would tend to do, I think, what most people would do, is they would just look at the equation and just say, well, there's x. This is my definition of x. So plug in x. And then take x dot, and you would have two terms by the product rule. Right? Because you'd have an r dot cosine theta plus, and then you have a term with r, and then you differentiate this with respect to time, blah, blah, blah. That will work. And then in the end, you'll have to solve for r dot and theta dot. And it takes a little more algebra than the way I'm going to show you. The better way is to just use this little identity that x squared plus y squared is r squared. And so if I differentiate both sides with respect to time, and in all of this, please keep in mind, everything's a function of time. Do not forget the chain rule term that will come from that fact. So take d dt of x squared plus y squared, and say that's d dt of r squared. And now on this side, we would get 2x x dot, where x dot is one of these chain rule terms that I'm talking about, plus 2y y dot. And then that would equal the derivative of this with respect to time, which is 2r r dot. So we get this nice equation that r dot times r is xx dot plus yy dot, where I've just canceled out the 2 on both sides. So that's a handy little identity in polar coordinates, and it's going to make our system look very simple. That is, if we take the x dot and y dot in our governing equations and plug them in, watch the nice things that happen. Well, all right, what are the governing equations? We have x dot is negative y plus ax, and then the x squared plus y squared, we might as well write as r squared. And likewise, y dot is negative x, no, not negative, just ordinary x, plus x plus a y r squared. And then, do you see it? See the nice things happening? We go r, well, I wrote r dot r. That looks funky. R dot would be x dot. Let's just laboriously write it out. X times x dot minus y plus a x r squared plus y dot. So then I go x plus a y r squared and simplify that a little. Notice the xy terms cancel out. One's a positive xy, one's a negative xy. And we're left with a, the x squared plus y squared factors out all times r squared. So that's just ar to the fourth, right? Because this thing in here is just our friend r squared again. And so r dot is ar to the fourth. That means r dot is ar cubed. Wow, that looks pretty clean. So guess why it came out that cleanly? Because how did I cook up the system in the first place? I started with this and then put it into Cartesian coordinates. Okay, so that's what I said. Oh, come on. It's contrived. It's meant to be, it's cooked up to be nice. So I'm trying not to lie here. That's how it was constructed. But okay, fine. It's very pretty. Now what about the theta dot? We're not done because we need another equation. Do you want to ask anything about the r dot manipulations? You're okay with that? So the theta dot analogous manipulations, well, for those, the best move is probably to say something like theta is inverse tangent of y over x. And then let me skip some of the algebra, but maybe just check for yourself at some point that this implies that theta dot will be xy dot minus yx dot all over r squared. So that's the conversion into theta dot. So check that. You have to remember how to differentiate inverse tangent. Oh, all right. Well, anyway, taking that for granted, then let us substitute everything in there, and we get, all right, let's write it out. Theta dot is, it says x, y dot. So y dot is up there. It says x plus ay r squared. Then I go minus yx dot, which would be minus yx dot is minus y plus ax r squared. And then the whole thing is over r squared. So what's happening here? It looks like I'm getting x squared from there. From here I'm getting plus y squared. And then I have a term that looks like a xy r squared that cancels with this term, a xy r squared. So this boils down to x squared plus y squared over r squared, which is 1. Wow, isn't that interesting? So that also came out very nicely, again, by being constructed that way. All right, fine. So we now have this very simple equation or system in polar coordinates. R dot is ar cubed. Theta dot is 1. And notice a nice thing about it, which is that it is the r equation is decoupled from the theta equation. Whereas with the xy representation, the x and y were all coupled together. So these are actually, you could sort of think of these as two different one-dimensional systems. independently. The r is doing its thing, and the theta is doing its thing, and they don't know about each other. And so we can use our one-dimensional system technology that we developed earlier in the course for thinking about what's going to happen. But also, you could just use common sense. Just think about a typical point. Let's try, say, for instance, what happens if A is negative in the xy plane? What's the trajectory going to look like from some typical initial condition? Well, first of all, theta dot is 1. That just means the theta is going to keep increasing. That is, it's going to keep moving counterclockwise at a steady rate. Meanwhile, in the radial direction, since A is negative, r dot will be negative, and so the radius will be decreasing. So imagine the motion of something which starts somewhere, moves around at a constant angular velocity, but with its radius decreasing. It's going to look sort of like that, right? It's a damped spiral, a stable spiral at the origin. And if A happens to be exactly 0, then we really do get a center, because if A is 0, r dot is 0. That means the radius doesn't change. So whatever radius we start on, we just stay there, which means we move in a perfect circle. And that's true wherever we start, except if we start at the origin, then we'll stay there. But all other trajectories are just, perfect circles about the origin. So for A equals 0, the linearization gets it right. But that's not too surprising, since when A is 0, the cubic terms are gone and the system is just linear. So, of course, the linearization works for a linear system. And then when A is positive, you've got an unstable spiral, because now the radius is increasing. Okay, so you can see that the linearization doesn't know any of this. It's doing its best to, with what information it's got, but it cannot predict the existence of this stable spiral or this unstable spiral. So is there any question about this example? If you want to think about it intuitively, what's the lesson here? As I said, centers are delicate. And you can kind of understand why they're so delicate. That is, they're delicate in the sense that they're easily altered by nonlinear terms. Even very tiny nonlinear terms. Now, why is that? It's just, think about it. Suppose I have a trajectory that's trying to be almost circular, almost closed, as would happen around a center. So I come around, and then I just happen to barely miss. Can you see that that isn't closed? I've drawn it so that the trajectory is just a little bit inside where it started. Well, once you're there, now because of the fact that trajectories can't cross, you're kind of hemmed in. That is, you're sort of forced to just keep swirling around like this, and you can't get out. Now you're really destined to be a decaying spiral. Even if you just miss by a nanometer. So that's the point. Okay, so centers are delicate. Now, having said that, when we run into a center according to the linearization, you've got to have some kind of like alarm system that goes off. Whoop, 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 right? You're not going to necessarily believe in the center unless there's further evidence. So I'll probably make that sound from time to time to remind you. Also, just because it's fun to make weird noises. So, all right, now let's do an example of phase plane analysis where we use, I don't want you to over worry about centers and such, because most of the time they won't come up. It'll be the other types, the non-borderline cases. And so in this next example, that's what we're going to see. So section 6.4 in the book. By the way, there's a little question that came up on our Piazza page today. Do I really mean that the homework is not due Thursday? It's due a week from Thursday? Yes, I really mean it. So it's due February 20th. And that's because we just have more stuff to do before it's time for the next homework. Also, you have a break coming up, and I'm not supposed to assign homework over the break. So you ought to do your homework, then take your vacation, or do it when you come back. But don't work over the break. That's illegal. All right? You're allowed to, I suppose, but I'm not allowed to assign anything then, and so I have not. Anyway, section 6.4 in the book has to do with what I'm going to refer to as rabbits versus sheep. So it's a simple model of competition that goes back to scientists named Lotka and Volterra. So competition between two species. Now, don't get confused about what competition means. Competition is not predator-prey. So the sheep do not eat the rabbits. Right? The sheep eat grass, and the rabbits eat grass. So they're competing in that they want to eat the same thing. They have the same resource that they like. And so think of them, as I say, competing for grass. And I'm going to kind of make up some stuff here, but it's approximately right. That is, first of all, we're going to think of both as continuous variables. So x of t, the population of rabbits, it's really discrete. There's no such, well, I guess there could be a fractional rabbit if wolves were involved, but we're not doing that problem. Think of rabbits as whole numbers of rabbits, but we're going to pretend they're continuous, just for the sake of doing differential equations. And we'll let y be the population of sheep. And, of course, they're both positive, or non-negative anyway. xy greater than or equal to 0. And now let me just write down a simple system with some whole numbers in it. X dot equals x times 3 minus x minus 2y. And y dot is y times 2 minus x minus y. So this will be our assumed governing equations. These are not like f equals ma. They're not derived from any great deep principles. We're just making them up, that they're supposed to be sort of plausible. And so let me tell a little story to make them sound kind of plausible. Okay, so if the idea is that these, let's think about, say, the x dynamics, the rabbits. So if there were no sheep, you'd have x dot is just 3 minus x times x. And you should recognize that kind of equation. That's a logistic equation, right? Where for a single species it would grow. We know that this kind of thing would just grow up to a level of 3. Now 3 doesn't mean 3 rabbits, because that might be a little bit silly. Maybe think of it as 3,000 rabbits that can live on some patch of grass somewhere in a field or something in somebody's farm. I don't know. So don't worry about the units too much. So 3 means something, the size of the carrying capacity for the rabbits. Think of it as 3,000 if you want. Then there's this term which reflects the presence of the sheep. Now notice it's a 2xy. And notice it's got this negative sign. So this is a kind of death rate happening to the rabbits due to the presence of the sheep. Now what does that mean? Since I said they're not directly eating the sheep. But they are, sorry, they're not directly eating the rabbits, but they are eating the rabbits' breakfast. Right? They're eating grass that the rabbits would like to eat too. And so that we assume, first of all, well, we assume that causes an increased death rate for the poor little cute rabbits. But also, compare what's going on in the sheep equation, where you've got y dot is y times 2 minus x minus, did that wrong, 2 minus y, I mean, and minus x times y. Right, if I expand it out a little bit. So this says that the y, the sheep, will go to some level called 2 as opposed to this one going to 3. So you might say because, hey, rabbits are good at reproducing, right, famously. And so they have this high growth rate, this 3 times x compared to the 2 for sheep. So the rabbits have the edge in that they're faster at reproducing. On the other hand, the sheep have the edge in that they're big and mean. And when there's an encounter between a sheep and a rabbit, which occurs with, you know, if they're sort of well mixed and they're all over the place, think of it like chemistry. You might have learned a thing called the law of mass action, that the rate of reaction is proportional to the concentration of this stuff times the concentration of that stuff when they're banging into each other. So this x times y is proportional to the probability that a sheep meets a rabbit, in which case there's trouble, and you know, maybe the sheep pushes it. I don't know what they do exactly, but it's worse for the rabbits when that happens. And so that's why there's the 2xy for them, but the xy for the sheep. Okay, so that's all made up. But anyway, this is actually a model you can learn about in an ecology course. And it's the simplest model of competition. So now, how to analyze it. Do you want to ask anything about it before we? No. Okay, so fine. It's a bit simplified, and you can make it more complicated, but let's just look at it. Anyway, so first let's find the fixed points of it. And to do that, it's probably easiest to look at it in this factored form over here. That is, we're looking for when the right-hand side is 0. And there are 4 possible ways this can happen, right? We could have the first terms, x and y, could both be 0. Or like this x could be 0, but the second term here in parentheses could be 0. Whatever. So there's various cases. And trying out the different cases, you'll find that the fixed points are 0, 0, 3, 0, 0, 2, and 1, 1. And that's it. The 1, 1 case, for instance, is when we're saying this parenthesis equals 0 and this parenthesis equals 0. If you solve those two simultaneously, you'll get 1, 1. All right, now let's linearize around them to see what's going on. Well, so we write down our Jacobian, partial x dot partial x, partial x dot partial y dot partial x, partial y dot partial y. And so you have to kind of calmly and carefully take those derivatives. And if you do that, you'll get 3 minus 2x minus 2y minus 2x in this corner minus y down here, and 2 minus x minus 2y. And all of that is evaluated at whichever fixed point we're talking about. So let's start classifying some fixed points. All right, so at 0, 0, the Jacobian reduces to just a diagonal matrix. A becomes 3, 0, 0, 2. And that's a pretty easy one to look at. We don't have to do our whole thing with the tau and delta, since when it's diagonal, we could just read off the eigenvalues. They're sitting right there on the diagonal. So we have a lambda 1 of 3 and a lambda 2 of 2. And since they're both positive, that tells us we have an unstable node. Then we remember that unstable nodes are not borderline cases. So that's for real. That really is going to be an unstable node at the origin. We also talked when we were doing linear systems about which way the trajectories leave a node, along which, the slow direction or the fast direction. And so here, the principle, as before, is that the trajectories leave along the, in this case, it would be the lambda 2 equals 2 direction, since they always leave along the direction corresponding to the eigenvalue closest to 0. In this case, absolute value of lambda 2 is nearer to 0 than the absolute value of lambda 1 is. So we have to figure out what is the eigendirection corresponding to lambda 2, and it's just 0, 1. For a diagonal matrix, you could just see that. So the eigenvector V2 corresponding to lambda 2 is the vector 0, 1. And so the trajectories, here now I'm in the xy plane. Here's x, rabbits. There's y, sheep. So we're in the neighborhood of the corner down here near the origin. And the linearization is saying this point is unstable, but we're going to tend to leave along that direction. So you would expect the trajectories to look sort of, they're going to look nodey. They're going to look kind of like this in the neighborhood of that point. Others similarly. So that's the flow near that. And what our strategy here is we're going to try to make a bunch of little pictures near each of the fixed points, then put them on the whole plane, and try to plausibly connect everything. So it's not a proof, but it's meant to be reasonable. Any question about what I have up till this point? All right, so let's look at these other fixed points. That was 0, 0. How about 0, 2? So near there, well, at that place, the Jacobian comes out to be -1, 0, -2, -2. And that matrix is triangular. Right? It's got all its stuff in there, and there's a 0 up on the top. So that actually is also one where you can read off the eigenvalues by just looking at the diagonal. And so this has lambdas equal -1 and -2. And that means that's a stable node. The trajectories approach the stable node along the lambda equals -1 eigendirection. Which you can compute is 1, -2. Let me write it this way, which is v, the vector is 1, -2, like that. So I'm taking for granted here that you know how to do calculations of eigenvalues and eigenvectors of 2 by 2 matrices. Okay, so you could check that if you want. But anyway, so 1, -2 would look sort of in the neighborhood of this point. We're saying 0 on the x-axis, 2 on the y. 1, -2 is something which goes over 1 and down 2. So it sort of looks like this. But remember, it's a stable node, so we're coming in like that. And so the trajectories are going to approach that eigenvector. And then from the inside, they would also go, like that. So that's the local flow near that point. Or that's 2. Okay, so hopefully you're getting the hang of this. Let me crank out the other 2 points and then put it together. All right, 3, 0. Well, there, the A is -3, -6, 0, -1. Another triangular matrix. It has lambda of -3 and -1. Again, a stable node. And near that point, you can check that the flow looks about like this. And then the final point is 1, 1, which there we don't actually get a diagonal or a triangular matrix, so we have to do a little bit of work. Here the A comes out to be -1, -2, -1, -1. And so if you check the determinant of that, you'll get 1 minus 2, which is -1. And as soon as you see a negative determinant, you know it's a saddle point. And saddle points are reliable, right? We know from the linearization they're not borderline cases. So the saddle point, and these, I should have said, these other stable nodes are equally reliable. So linearization works for us. And if you check the eigenvectors of this matrix, you'll find that near 1, 1, the flow looks like this, approximately. That the inward direction is sort of like that, and the outward direction is kind of like so. Well, I'm drawing this one as an open dot because it's unstable, right? I mean, trajectories will go away from there, typically. Okay, so we have these 4 pictures now. Let's see, are they all still on the board? Yeah, they all are, right? So there's 1 up there, 2, 3, and 4. Let's put them all on one picture now. So let's put it all together. And we get sheep are over here, rabbits here, coming out like that, going in here, also going in down here. And then there's a saddle in the middle that looks kind of like so. That looks sort of funky. That's supposed to be, you know, a little straighter looking maybe. And then it's got some saddle-y looking stuff there. Okay, so from the fixed points alone, we can draw that amount of information. We could also observe other things. Maybe we should. It's worth commenting about what goes on if we're stuck on one of the axes. That is, if, like, say, x is 0. Let's just look again for a second at the equation. It said x dot was x times, what did we have? 3 minus x minus 2y. And y dot was y, 2 minus x minus y. I just want to make one more remark about all this. Suppose you had x equals 0 at some time. So if x equals 0 at some time, that is to say, we're on this axis. All right, that's where x equals 0. Then notice that according to this, if x is 0, at the next moment, or at that moment, x dot will be 0. That means the x won't change. And you can convince yourself by thinking that way that if you're on the x-axis, sorry, if you're on the y-axis, you will stay there for all time. Which is, all that's saying biologically is, if there are no rabbits, there will never be any rabbits. Right? Makes sense. They don't come out of the atmosphere. And so that says that these straight lines, the axes, are, so to speak, invariant. So if x is 0 at some time t, then x of t equals 0 for all t. So we would say the x-axis is invariant. And that's a useful thing to do, to notice in problems like this, that if you can find invariant lines, they also give you some feel of what's going on in the phase portrait. Like here, if we're above, then we're going to just come down on that invariant line. Likewise, the x-axis is itself invariant. So if we start there, we'll just move to this point from either side. OK, so anyway, having said all that, now, can we plausibly connect everything? I think you'll agree that there's only one. Well, we could think about it a little more rigorously, but it seems like there's only one reasonable way to connect everything. And then I want to draw some conclusions about this. I mean, it's not just math. We want to say something about our little story of the sheep and the rabbits. Make some predictions. All right, so does it seem clear what's going to happen? Maybe it is. I don't know, like think about a trajectory coming out of the neighborhood of the origin. Where can it go? Or actually, maybe even better to do. You know, the saddle points are very informative. What if you think about the saddle point? Think about the trajectory, say, there's a trajectory that was going into the saddle along the eigendirection, the stable eigendirection. You could ask, where does that come from? You know, going backwards in time. Doesn't it seem pretty clear it has to come from the origin? I mean, it can't come from either of those other two fixed points because those fixed points are attracting. Stuff goes to them in forward time. So I think you could believe that this trajectory has to come from here. And pretty much once you've drawn that, the rest of the picture is almost decided for you because like this trajectory is going out. Where's it going to go? Well, I think it was going to go right there. Now, not on a straight line. There will be some curvature to it. Likewise, there's some point down here where there's a trajectory that goes down there, and I'm trying to draw it with a little bit of curvature so you don't think these are all straight. And then it seems like there's something else, you know, that has come in kind of from infinity to this saddle from over there, from the northeast. And these other trajectories, you know, are going to kind of do something like that, or like this, or like that, or, well, Yeah, this is a little confusing, isn't it? Because we said all trajectories leave the node vertically. So maybe I should draw that a little better. I think this can't be right, what I drew, can it? That is, going back in time, everything has to be along they have to leave along this direction. So in fact, there's going to be something that comes like that. It's got to be a little more vertical here. Okay, but anyway, that's a detail. Except for the ones that are exactly on the axis. They are allowed to go that way. Anyway, so there's our phase portrait. I hope that seems plausible to you, or like something you could have drawn for yourself. And now notice what it's saying. If you focus on this curve here, the one that goes that actually in forward time goes into the saddle. The jargon for this is we refer to this as the stable manifold of the saddle point. You might think that's a bit fancy to refer to it as a manifold since it's just a curve. Yes, that's true. It is just a curve. But in higher dimensions, this thing might be a surface. So we keep the word manifold so that we don't have to change the word when we go to higher dimensions. But anyway, we've got this stable manifold of the saddle point. And notice that it sort of acts like a dividing line in the sense that anything that starts below it. So if I start indicating initial conditions with these dots, all these initial conditions have the same fate, right? Anything that starts below this is going to go down here to a world with global domination by rabbits, right? Whereas everything that starts above is going to be, sheep nirvana. The sheep will have driven the rabbits extinct. And so, that's an interesting thing. Who wins? We said both the sheep and the rabbits had their advantages, but it turns out that who wins depends on the initial conditions. Below the stable manifold, as I say, the rabbits will take over the world, and above the sheep do. And then there's this exactly, very special case right on the stable manifold when they could coexist. That is, they will both come in, and then you'll have coexistence of both. But you'll notice that that's kind of unstable in the sense that if, there's just one extra rabbit or something, some little perturbation will knock you off that manifold, then you're going to go one way or the other. So it's not really stable to that kind of disturbance. And whereas these other states are stable in the sense that a little disturbance, you'll still come back. So the biologists talk about a principle of competitive exclusion, that you can't have these two species coexisting stably if they're occupying the same niche. They're both grass eaters. Somebody's going to drive somebody extinct. And that's often found to be true in the real world. Yes?
Can you find an equation for this curve?
It's a good question. Yes, the question is, can we find an equation for this stable manifold? There are ways of approximating it, like with power series in the neighborhood of this point. It's not so easy to calculate it exactly, although it may be possible in this example. But in typical examples, you wouldn't be able you wouldn't have a hope of getting it exactly globally. Yes? Well, when I say the x-axis is invariant, I mean if you start on the x-axis, you'll stay on the x-axis forever. That's what invariant means in dynamical systems. It always means if you start on a place, you'll stay there forever. Hang on one second. Sorry, what was the question?
We have a fixed point that's on the axis that we're approaching.
A fixed point on the axis.
We wouldn't have uniqueness, right?
Wouldn't have any what?
Uniqueness?
Well, that wouldn't violate the invariance, right? I mean, if this point is also on the x-axis. So if we start here on the x-axis, we'll stay there. We'll end up at that point on the x-axis.
Right, we don't start off on the x-axis.
If we don't start off on the x-axis, we will either asymptotically approach this point or that point, or in rare cases, this point. Yeah. Yeah.
So if you say instead of a stable fixed point on the x-axis, you have a stable fixed point, but you still have that invariant condition?
Yes. Okay, so the question was, suppose we had an invariant line, but with an unstable point on it.
Yeah.
So then you can have a situation like that where you might, be repelled away from this point towards some other point, but it would have to still be on the invariant line. That can happen. So yeah, so I'll be occasionally assigning exercises to show this or that line is invariant. Yes?
So say that was a saddle point instead.
If this were a saddle point here, so then let's suppose we have something coming in like that.
Or
Coming in and going out, but we are coming in and going out.
on the other, so say you're coming in on the axis.
Coming in on the axis like this and going out like that.
Yeah.
Yes?
But if your x-axis is still invariant,
Yes?
do you hit the point?
So here, if we started exactly, remember, we're not talking about, like in real life. This means mathematically exactly. If we're truly on the x-axis or this invariant line, then we'll just, be guided by the vector field to this point at infinite time. And you're worried because if you're just slightly above, you're going to go veering off. Is that your concern? That's true. But just as a mathematical thing, we're saying that there is this curve with the property that if you started on, or this line, if you start there, you'll stay there forever. That is a property of the picture. But they are sensitive in the way that you're worried about, that if you're a little bit above, you're not going to stay near that line. That's true. Well, let's see. We have a few minutes we could spend doing more stuff. On the other hand, it's not really a good time to start a whole new topic. So why don't we just stop there? All right. See you next time.